So good day. My name is Wong Zheng, machine number A202728. So today I'll be presenting my control simulation assignment. So for this assignment is we simulate a model of 3 CSCR with variable hold up. So this is just a simple background. And these are the CSCR parameters that is given to us. So first we will be the first question is to model the CSTR and find the transfer function. So for question 1, it's pretty simple. So we just need to we just list out all the assumptions. So basically we'll be forming two equations. The first one is the material balance and the second one is the energy balance. So first we form the material balance. So these are the assumptions. Basically fluid is perfectly mixed and liquid is incompressible, different volume CSTR, different inlet flow rates, constant heat capacity, constant heat produced, constant heat added, inlet outlet flow rates are constant, heat loss negligible, different order reaction. And note that the CSTR1 and CSTR2 follow the first order of reaction, and CSTR3 follow the second order of reaction. So we can then perform the general equation of material balance of CSTR. So basically, rate of accumulation is in minus out minus rate of reaction, which is the generation. So for component A, it can be expressed like this. And the general energy balance for CSTR is accumulation equals to energy in minus energy out plus heat added and plus heat produced, which is the generation. And it can be expressed like this. And then we perform the modeling of the first CSTR. So the material balance is just shown just as above, and we divide the whole equation by V1, and then by steady state, the differential part becomes 0, and then all things become steady, which then have a bar at top, and then we substitute equation 1.4 with 1.5 to get this equation, and then we introduce the deviation at around steady state. And then the equation overall become like this. So basically, with the bar upside become the variable with prime, and then we take the Laplace transform, and then we rearrange the terms, then we simplify it. Then we simplify it, and then we get this transfer function. So the overall transfer function is like this, and then we substitute the constant inside, and then we can get the transfer function for concentration for the first CSTR. So okay, it's just like this, and then we continue with the energy balance part. So the energy balance for CSTR1 is like this, and then we divide all the terms with rho CPV1, and then at steady state is like this. Then we substitute the equation 1.15 with 1.16 to get this equation. And for the deviation around steady state, so we introduce the deviation variable, and at the steady state, the bar terms becomes the prime terms. And first we find the transfer function with respect to Q. So then we assume T0 prime is 0 and CA1 prime is 0. Then we get this equation. Then we perform Laplace transform, and then we rearrange the term to get this transfer function and substitute into the variable. Then we can get the transfer function for Q1 in numerical form. Then we find the transfer function with respect to Ti minus 1. So at this time, we assume Q prime equals 0 and CA1 prime equals to 0. So then taking the Laplace transform, and we rearrange the terms, we can find that transfer function for the temperature term is this one, and then substitute into the numerical, and then we found the transfer function for T1. So the second CSTR is basically same as the first CSTR because They are both in first order, and yeah, so first order, nothing special. So basically, it's the same part, it's the same term with the variable shifted to first to second. So basically, you can see this is the material balance part, and this is the energy part. So for the third CSTR, the things will be different a bit because the concentration is in second order. So we will need to perform linearization by using Taylor expansion. So at this part, you can see we perform Taylor expansion and linearize the square part into a linear form. So basically, this is our linearized term. And then we substitute this linearized term into the equation, and we can get the transfer function for material balance is linearized. So this is our transfer function for the third concentration. And then for the transfer function for Q and temperature for the CSTR3 is also same. We also need to perform Taylor expansion and linearization. And then substitute into the numbers, and we can get the transfer function for Q3 and T3. So then we can find the overall transfer functions for concentration, which is the material balance. Since from the question given, we know that the three tank is non-interacting, so we can say that the overall transfer function for concentration is just the it's just a sum of multiplication of all the CSTR, and then we found that the overall transfer function for material for the concentration is like this, and for the overall transfer function of heat, although the system is non-interacting, but we can observe that if we multiply these three terms together, it won't become in T3 prime over Q prime expression. So we assume that the heat is added into the third tank only, as it measures T3 as the final temperature. So the other CSTR transfer function for heat are assumed to be disturbance. So this is the overall transfer function for heat headed, and for the overall transfer function for inlet temperature is the same case as concentration, because it's not in interacting form, and we found that it can be reduced into this form. So overall, it becomes like this. And then the overall equation for energy balance around the final temperature can be expressed like this. So this is very important, as this equation and the concentration equation will be used for the transfer function for simulation. So move out on question 2. So the block diagram. So basically, we need to form the block diagram in Simulink. So for my case, we have two equations. So basically, we need to model two feedback loops. One is concentration, and one is temperature. So basically, one is material balance, one is energy balance. So for the energy balance, you can see the overall block diagram is like this. So we have input, and then this is the controller, this manual controller. And here we put inside the load, and here is the overall process for energy balance. And here is a figure of merit. And at here we can put a scope to observe our output signal. And for the mass balance is basically the same, just the process we swap into the material balance form. Right. So for question 3, we need to design the control system around using P, PI, and PID, and then test the controller based on servo and regulatory control. So we'll be using Simulink for this case. So for the temperature case on servo control, we will be the input. So since servo control, there is no load, right? And the input for the temperature in servo is shown as this. So the initial is 30 and the final value is 35 and the step time is 1. So we run for 50 stop time. And we can see the simulation outcome. So there's no disturbance in this case. So this is the manual using the manual controller. And for the toolbox case, is here. There's a toolbox case. And the error are shown as this one. So this is P. This is P's error. So it's quite high. And for PI, it gradually decrease as we go to PI and PID. So this is PI. And this is the error for PID. So the manual and using manual and toolbox is basically not quite such a difference because they're mostly using the same algorithm. So this is the manual controller for P for temperature, PI for manual, and PID for manual. And for the concentration part, the step inputs are shown as here. So the set time is 1, initial value is 0, and the final value is 0.3. And this is the error for P for manual controller, P controller. This is manual controller PI. And this is manual controller PID. And the outputs are shown as here. No disturbance. So here are the outputs for concentration. This is manual. And the output for toolbox is here. And then we'll repeat the whole process by introducing the load, which is a disturbance. So the load for temperature is set to the step time is at 25, and we put our final value as 5. And for the concentration part, the step time is the same. It's 25, but the final value is 0.5. And then we run the simulation at the same stop time. And note that all the controllers have the same, all the P, PI, PID controller have the same gain value. So the gain value are shown as here. So for P is 0.6, and the I is 0.4, and the D is 0.625. So this is when we added the disturbance. So you can see the disturbance is added here. This the output for temperature, and this is by manual. And by using toolbox here, you can see when the disturbance added in, the graph jumps a little bit, but is able to get back to the steady state. And for concentration manual, it's also the same. Disturbance added in and then go back to steady state. And toolbox is here. So basically the same. When we added the load, the error will become higher a bit than in the servo case. So basically this is the regulatory case. So you can see the p-value, the error for p controller, error for pi controller, and error for PID controller. So it's getting smaller if you increase the I and D inside the controller. Okay. So this is for question 3. So the summary of this finding is basically the PID controller is generally greater in all cases because even though for temperature control it's better to have lower ISE value, and for the concentration is lower ITAE, but overall PID controller can get these two values at a lower rate instead of P and PI. So basically just use PID controller. And for question 4, we need to repeat question 3 with multiple set point disturbance. So for multiple set point disturbance is here. You can see that we have 3 set points for the input and 3 set points for the load. Okay, so here we start from the regulatory case because I already put in the we already put in the disturbance value. So for the disturbance value for temperature, the expected inputs we first wait, yeah, okay. The expected inputs for temperature is T equals to 35 degree when T is equal to 0, T is 50 when the time is 25, and T is 65 when time is 70. So basically it's a 15 degrees increment for every step. And the expected inputs for concentration is 0.3 mole at T equals to 10, at T equals to 0. And then the concentration rose to 0.7 mole when T is equal to 25, and then drop to 0.5 mole when T is equal to 70. And for the temperature load, it's set to +5 at 15, -20, -12 at 35, +8 at 55. For concentration, load is set to +0.5 at 50, -0.12 at 35, and +0.8 at 55. Okay, so then we can run. And we can get the results. So this is the temperature for regulatory and no toolbox. As you can see, the disturbance is added asynchronously with the set point. So basically, the disturbance at the set points are not having the change not at the same time. So this can make the controller to be challenged a bit to get back to the steady state. But as you can see, PID controller has successfully to get back to the steady state even when the disturbance are crashing into the system. So P and PI not so great. And for the concentration part, it is also the same. You can see the disturbance at set points are increasing and decreasing at the different points. And also the PID, you can see the PID controller also managed to settle down to the steady state faster than P and PI controller. Okay. So for the servo part, because I need to put back into 0, it's a bit tricky. So I just show the report, the screenshot of my report. So this is the response curve of multiple servo control temperature. So this is a manual part. You can see every jump it managed to settle down back to the steady state for P and PI, for PI and PID, but P have offset a bit. and this by using toolbox. For toolbox, the oscillatory for PI controller is quite bigger, and this is a concentration control for manual at servo. So basically, settles PI and PID settle back to the steady state, and P have the offset. And for using toolbox is the same case, but performs greater lah, but compared to manual. So the summary findings of this part is also using PID controller is better because it also provides lower error values compared to P and PI controller. And question 5 need us to tune our controller using two tuning methods. The first one is Ziegler-Nichols, and the second one is Kuhn. So the Ziegler-Nichols tuning method is first to turn the controller in P-only mode and increase the controller gain until the loop start oscillating. And then we can mark this critical value as KU and the period of oscillation as PU. And then after we get KU and PU, we can refer to the Ziegler-Nichols tuning table to find the optimum Kc, tau I, and tau D parameters for P, PI, and PID controller. So the tuning table is as shown. You can see for each P, PI, and PID have different parameters to insert. So first we perform the tuning for temperature controller. In this case, we are all using manual toolbox controller and in servo case. So for the ZM method for temperature control is like this. And then we need to increase our stop time to show a bit. Okay, let me comment out. So for Ziegler-Nichols method, so we increase our stop time to 200 and let we run the system. Okay. So this is the temperature control. You can see the graph starts oscillating. I'll create this graph. Okay. Basically, you can see when the graph starts oscillating at a constant period, and then we can find the KU value. So for temperature is 1.278, and for PU is for the period of oscillation is 5.636 seconds. And then we use these two values to tune our PID controller. And the tune measurements are shown as this curve obtained. This is the toolbox servo control for temperature. And the values of this part is slight improvement in P and PID controller when compared to the previous part when we haven't do the tuning. So this proves that this tuning method is effective in the temperature control. And for the concentration control, it's also the same. We increase our gain to get this oscillatory graph, and then we find the peaks. We find the peaks to find the oscillatory period. So for this is 4.85, and the temperature curve and the ultimate gain is 2.283. And the tune Ziegler-Nichols settings for concentration is like this. So when we insert this one, we can get the response curve for servo control concentration after tuning. But if we compare to question 3, the improvement is not as much as the temperature one, because the concentration error is already quite small compared to the temperature one. So next is the Kuhn-Kuhn. So the Kuhn-Kuhn is another type of tuning method, and the procedure is, first we need to let the system to reach the steady state, and then after that we introduce a small step change after the controller output to get the S curve, or known as the process reaction curve, and then we draw a straight line at the tangent to the curve at the point of inflection, and we find the following parameters. First is TD, and then second is T, and then the third one is KP. And then using these values, we then substitute into the Kuhn-Kuhn table in here. So we can see all the different parameters for P, PI, and PID. So the temperature control is as shown as here. I'll open my Simulink. So this is an open loop tuning process. As you can see, the controller is out of the equation, and then we input a set signal to get the graph. So you can see that the reaction curve is like here. So you can see when the process reaches the steady state, after we input a signal, it rises again to get this S shape. So then we can get all the parameters in this S shape. So this is for concentration. And no, this is for temperature. For concentration is here. Concentration only have single rise. As you can see, when we input another signal here, the reaction curve also rises until it reaches a steady state point. So here are the parameters for temperature, and then we refer back to the Kuhn-Kuhn table, and then we can get back the new Kc, tau I, and tau D values. And then we insert back into the equation, we can get the graph does not look very good because the Kuhn-Kuhn tuning is probably not suitable for temperature control. So not effective lah in this case. And for the concentration controller, we repeat the same thing. And then we get all the parameters from the S curve, and then put into the Kuhn-Kuhn table. Then we can get the parameters of Kc, tau I, and tau D. And then we substitute back into the Simulink. And this is our response curve after the tuning process, which is also not good for concentration control. So overall, the Ziegler-Nichols tuning is better than Kuhn-Kuhn in my project in this case. So the last question is to propose an advanced process control strategy and design in the system. So for my part, I propose the model predictive control (MPC) because it can overcome the limitation of conventional PID control. So this MPC is explicitly account for multivariable coupling and operating constraint, and this can result in reduced temperature overshoot and faster concentration settling. So for the MPC setup, I only put for the temperature control. So it looks like this. So this is the MPC controller. It's different than PID controller because it needs to do some manual it needs to do some manual tweaking, but not like put the input. It's not like you need to find the gain values for each part. You can manually tune it and then see how the output becomes inside the controller. So I have already tuned my controller in this scenario. So you can see the output response. The curve is much smoother than PID controller, and the gain is not as high. See, the gain is only this high only. So overall, this controller strategy is much better than PID controller. Okay, so I think that's all from me, and thank you very much.